Hi everyone. Today we will be talking about waves from a P12 AQA physics topic. We'll start firstly with what is a wave. You're used to seeing waves in sea and or the Mexican wave that they create in football and so on. So we're going to look at more of the details there. But a wave simply does one thing. It transfers energy or information, in this case when it comes to your phones. I'll go into it more later. So waves transfer energy. The most important part here is when you do describe what waves do, you have to state that they transfer energy, but no matter. So matter doesn't get transferred. When I talk about matter, we mean particles that make up. So particles could be, for example, water molecules in sea waves. They could be in salt molecules. There could be anything that creates the structure. So waves simply transfer energy through vibration, but they do not transfer matter. And I will explain that in a bit. Now we can classify waves in two different categories. One of them being mechanical, and the other one being the electromagnetic waves. What makes them different is the way they travel, so what they travel through. So mechanical waves are simply vibrations that travel through a medium. A medium is simply any substance. So for example, water, air, solid as well, solids. So anything that is made up of matter, anything that's made up of particles. On the other hand, electromagnetic waves are vibrations that travel through a vacuum. So vibrations that travel through vacuum. Now what is vacuum? It's simply an area where there is no existence of any particles on air or anything. So there are no particles at all. It's empty space, what we mean by empty space. So these are the two different types of waves that you can have. But then we have to also look at some examples. So mechanical waves could be, for example, sound waves. Sound waves have to travel through a medium. They have to travel through air. Water waves, once again, they have to travel through a medium, which is water particles. Waves on springs, so once again, the waves created on a spring travel through the metallic part of a spring or even the rope. Seismic waves as well, they travel through the Earth's particles that make up the Earth. So all of the mechanical waves require a medium to travel through. So like we said, anything that's gas, liquid, solid, anything that's made up of particles. Electromagnetic waves, on the other hand, travel through vacuum because they're simply vibration of electric and magnetic fields. They do not need any particles to travel through. They simply transfer energy and information without the need to travel through any particles. Examples include light waves, so what we see using our eyes, lights. Radio waves, which we use a lot in communication. So when you receive a text or listening to your radio or all these things that you tend to do, it's because there's information being received by your phones without the need of any air particles. Microwaves, they heat up your food, and that's because they cause the water molecules in your food to actually vibrate as they carry energy towards them. So we will see this in more detail as we go through the course. I wanted to bring back your attention to the specification here. Now, even though it doesn't mention anything in the specification yet about mechanical and electromagnetic waves, you should be aware because you will be asked to state whether a wave is mechanical or electromagnetic, as you can see here, and you should also be able to compare mechanical and electromagnetic waves, if you want to get 5 to 7 grades, or you should be able to compare how the particle nature of waves differs from the field nature of EM waves. We will come across near the end of this topic to make a bit more sense. So the first thing to pay attention to is in the specification says waves may be either transverse or longitudinal. So what do we mean by transverse? What do we mean by longitudinal? So what are transverse waves to begin with? So transverse waves are simply oscillations that are perpendicular to the direction of energy transfer. Now, if I had a string or a rope or a slinky, just draw a slinky. So let's assume this is a slinky. Now, if I started oscillating it up and down, so straight away up and down, then the slinky will start oscillating up and down, creating this transverse wave. Now, what I'm seeing here is if I placed, for example, a dot, like a marker on one of the coils of the slinky, that part will be moving up and down, just like my hand is, just like I'm shaking it up and down, but without moving along it. That's what we mean by waves transfer energy. So energy is being transferred in this direction, but matter does not get transferred. The matter is actually oscillating perpendicular, so this is 90 degrees, to the direction that energy is being transferred. So while I'm oscillating it up and down, each individual coil of the slinky is moving up and down only, and the energy is being transferred in this direction. So 90 degrees to it. That's what we mean by perpendicular, 90 degrees. Once again, a very big note is that this point or this point or this point, they're not moving along the rope. They're not moving in this direction. It's the energy being transferred. The particles are just simply moving there. So that's why we said, but no matter moves. So no particles are oscillating in any other direction. So a few examples of transverse waves. Firstly, to make it very clear here, all electromagnetic waves are transverse waves. So this is the easier one to remember. Mechanical waves can be both transverse and longitudinal. And we can give examples in a second. Now, water waves are actually transverse waves because the waves have oscillations. So this particle, for example, in a water wave is oscillating up and down, whereas the energy is 90 degrees to the other direction. So all electromagnetic waves, including light, radio, microwaves, X-rays, gamma rays, they're all transverse waves, and they belong in the category there. And also water waves, the slinky wave as well that we just mentioned is a transverse wave. So as long as the oscillations, the particles are oscillating at 90 degrees to the direction of energy transfer, they're considered transverse. Now we're going to go into what are the longitudinal waves. Okay, so what are longitudinal waves? They are simply oscillations that are parallel to the direction of energy transfer. If we look at the example again of the slinky, if I have the slinky like that, that means I have to oscillate it in and out. So push it in, push it out, and it will create areas where the coil is closer together and areas where the coil is further apart. We call these compressions, where the coils are closer together, and rarefactions when they're further apart. Like we said before, in terms of transverse waves, longitudinal waves have the particles oscillating in a different manner. So, for example, this is the point before I start oscillating the slinky in and out, and this is when it's oscillating already. So this coil of the slinky is going backward and forward along an equilibrium point. So this is where it originally was, and now if I'm oscillating it in and out, it will vibrate in that direction, and the energy transfer is in the same direction. That's why we say that the oscillations are parallel, because they are parallel. If the coils are oscillating in this direction and the energy is transferring in this direction, these two lines are in parallel. So we say that the oscillations are parallel to the energy transfer. Now, once again, to bring it back to the actual specification, you should be able to state that waves can either be transverse or longitudinal. The ripples on the surface of the water is an example of transverse. I didn't speak about an example of longitudinal waves, but an example of longitudinal waves is sound. That's the most important one. They have areas of compression and rare functions, which is very important. And always remember that since sound needs air to travel through, it's also a mechanical wave because it needs a medium to travel through. You should also be able to describe the difference between longitudinal and transverse waves. This can be done simply by using the definition of both and then making it clear that it is the direction of oscillation relative to the energy transfer that does that. And that you should be able to describe evidence that for both ripples on a water surface and sound waves in air, it is the wave and not the water or air itself that travels. That's very, very important. It is simply the wave, not the particles are involved in the process. The particles are simply vibrating along that fixed point that they started from. That's it. Just to break it down a bit with grades, if you are targeting to get 1 to 4, you should be able to state that waves transfer energy information but no matter. This is a very common thing that many people forget. You should be able to state whether a wave is transverse or longitudinal and whether it's mechanical or electromagnetic. Now, for you to be able to gain higher marks, you should describe how to use a slinky to demonstrate either type of wave. Simply like we said, it's just mentioning how you vibrate, how you oscillate it up or down or in and out. A diagram usually is very helpful to show that. Compare transverse and longitudinal waves and compare mechanical and electromagnetic waves. So those are the points we already mentioned. For a high grade, you should be explaining using the particle model compressions and rare functions of longitudinal waves. Now, in this case, when we mean with sound waves, especially, what you tend to have is when someone's talking, so let's assume this is someone talking. I know it doesn't look like a human, but imagine that's a human. Now, what you have is you have the particles in the air, and all you're doing is that you're causing a vibration of these particles, which in turn cause other particles to vibrate. You create areas that are close together, areas that are far apart, and then someone's ear collects the sound. We'll get to that near the end, but you should be able to describe how particles are behaving in that process. So this particle, for example, right here, will not end up being in your ear at all. It will stay there and just keep vibrating back and forward in this position. The same with every single particle. No one particle will end up being in your ears. You should be able to discuss particle behavior in transverse waves, and I will get to this last bit near the end of the topic. So let's move on to the next bit. Okay, so this second part of the topic involves the properties of waves. For example, amplitude, wavelength, frequency. These are new terminologies for some of you. Some of you might have come across them before, and some we use on everyday life without realizing. So the first thing I'm going to go back to is the transverse wave. So I'm going to start with transverse waves. And let's say I have a rope. So the rope is straight without me moving it. But once I start oscillating it up and down, I'm expected to get a transverse wave. So something like this. Now, paying attention that this is the rope with it being in its undisturbed position. So undisturbed meaning I didn't disturb it, I didn't move it yet. So I will set that line as this part here. So that's the undisturbed position. So obviously my oscillations created a transverse wave, and now I have these points here. This is called a peak because it's the top of the wave, and we call this a trough, which is the bottom of the wave. There's some key definitions here now to look at. So I'm gonna go to focus a little bit more here, and you can see that there's a definition for amplitude. So amplitude of a wave is the maximum displacement of a point on a wave away from its undisturbed position. Like we said, this is the undisturbed position right here. Sorry, right here. And the amplitude is the maximum displacement. So displacement being the maximum distance either upwards or downwards from the undisturbed position. So the maximum distance here from that point to that point. Please do make sure you show this clearly in your diagrams when it comes to exam questions. If you just do this, you won't get the mark. That's not the maximum distance. So amplitude is very important to take from edge to edge and show it. Then also I forgot to mention here that this is like taking a snapshot of a wave. So it's like taking, as I start vibrating the rope, I take a picture of it from the top, and then I can see it this way. If I was recording it, obviously this point, for example, will still be going up and down and up and down. So if this point was recorded, it will be moving up, down, until something eventually stops it. So going back to the amplitude definition, amplitude is simply the maximum displacement from the undisturbed position. If we look at what we mean by wavelength, this is one of the very important definitions as well. It is a distance from a point on one wave. So if I focus, for example, on this point, then it is the distance from a point on one wave to the equivalent point on the adjacent wave. So we have a look at that. What we have is the point distance from this point. So if this is one wave, then I have to find the adjacent wave. So the distance, that's the distance between the 2 points. So the wavelength is the distance between this point and that point. Just label the amplitude as well. So these are the key features you can see from a graph or a wave diagram that shows a picture of the wave at that moment in time and space. You might see this as a graph in certain occasions. So the graph will look like this. It will have a y-axis and it will be called displacement. Don't forget, displacement is simply distance in a certain direction. And then this line, the undisturbed position line, will actually be your x-axis, which is going to be called distance along the wave. So that's going to be distance. This is something that you should expect to see the graphs within. Then we have the frequency definition. This is actually should be easier for everyone because we do things frequently in a different way. So if I think about frequency in a daily a live thing that we do. So for example, we go shopping every week. That's how frequently I do my shopping. In this case, when it comes to waves, the frequency of a wave is the number of waves passing a point each second. So when I stated before that I go shopping once a week, I'm saying how many times I go shopping once, and how often, so once a week. In the case of waves, the frequency is the number of waves passing a point each second. So we can write an equation for this. So frequency is the number of waves per unit time. So time should always be in seconds for us to be getting frequency. You should also be able to state the units for frequency. So frequency has units hertz. Number of waves don't have units, it's just number of waves. There's no unit for that. We don't measure it with, oh, there's 20, I don't know, pascals. There's a unit for pressure, but we don't use it. There's no units for the number of things. So have, for example, 20 apples. There's no unit for 20 apples. But time has unit, and since frequency is per second, there's a unit which we call hertz. So we represent it as H, capital H and small z, and this is the actual way it's written. If I look at the diagram as well, I can measure how many waves are going up and down at this point, for example, for 1 minute, and then use the number of waves divided by 60 seconds, which is 1 minute, to find out how many are going through that point. We'll do example questions on that for you to understand it more. And then the next bit is the period, which is linked directly to the frequency. So period is the time taken for each wave to pass a fixed point. In this case, if I look back at the diagram, I need to just clear it out a bit. So if I go back to this, I need to consider how this particle is moving with time. So obviously it's not going to be frozen forever there. This is just a picture, remember, of it. So at one moment in time, it will look like this. After a quarter of a period, however, this point will be now there. So the wave will look different. After another quarter of a period, the point will be down there. After another quarter will be down there, and then it will end up back to where it was. So that's a complete period. This is what we mean by the time taken for each wave to pass a fixed point. So how long it takes for this to go up and down. You should be able to use the equation that links period and frequency together. This will be given to you, but you should be able to use it. You should remember that period. So period is for t, which is measured in seconds, by the way. Time always is measured in seconds, is one over frequency, where frequency is measured in hertz, and we already said that this is the frequency. That's all you need to be able to convert from one to the other. And if you want to rearrange it to make frequency, you just switch the position of these two. So it will be frequency 1 over t as well. The last definition of this part of the topic regards the wave speed. Now, wave speed is the speed at which energy has been transferred, but also you can define as a distance traveled by each wave every second, which is quite similar to the definition of speed in general, normal speed. So this is a distance covered per unit time. So we are used to that equation already, and if not, please make sure you remember that. So normally speed is distance divided by time. However, we're going to see now in this topic that for waves, we can also use another equation. Mind you, you can use both equations, this and this one here. It depends on what quantities you're given. It depends on what situation the question is set in. But all waves do obey this wave equation. So the wave speed is equal to the frequency times the wavelength, v being the symbol for wave speed, but the units are meters per second here. Frequency is represented by F, which is measured in hertz, so that's the unit. And wavelength is represented by the Greek letter lambda. You will probably see me writing lambda sometimes a bit different. It's just a Greek letter in the Greek alphabet, lowercase, and is measured in meters, because wavelength is a distance from one point of wave to the other point. So that's very important. You should be able to identify amplitude and wavelength given certain diagrams, but I will also show you how to identify period or frequency from a different type of graph as well. You need to memorize this equation right here. That will not be given to you, unlike the other one. So this equation needs to be memorized. This will be given to you, but you obviously need to make sure that you always double check your equation sheet so you know whether you have to use it or not. But the wave speed equation, you have to remember it and apply it when asked, and also to rearrange it. Just to make it a bit simpler for some people that struggle with rearranging, you can use a triangle where you have your wave speed, frequency, and wavelength. That way you can rearrange. So reminder that this means divide, this means multiply. So if I want to calculate wavelength, if I have the wave speed, I cover the part that says wavelength, and then I have wave speed divided by frequency. Or if I want to calculate, for example, frequency, and I have the other two quantities, and I have wave speed divided by wavelength. Alternatively, if I want to find wave speed, I cover wave speed and I have frequency times wavelength. Alternatively, you can rearrange. So I'm going to just use simply simples. This is the wave speed, frequency, and times wavelength. If I want to make wavelength the subject of the formula, then I divide both sides by the frequency, because this is multiplication. So I do the reverse. So I divide both sides by frequency. Frequency divided by frequency is 1. So wavelength is speed divided by frequency. You can do that for either wavelength or frequency. And this is something that usually students that want to get grade 7 and above tend to focus on. That will make a very huge difference if this pop up in the exams, is the displacement time graph for a wave. Now remember, before we said the displacement distance graph here doesn't involve any time. So I take a picture of it at any single time that I'm oscillating it, and I will get its shape. However, if I start recording how one of the points on the wave, so if I, for example, focus on this point here, like right at the beginning, so in the other graph here. Now this point is at this point in time that I was recording it, that I took the picture. However, it doesn't stay there. It actually moves up and down, we said. It goes constantly up and down. As time goes by, if I plotted that, so as time is going by in this direction, this is me recording it every, for example, second or fraction of a second, then that point will be here at one point, but then it will be starting here at time 0, but if after, I don't know, let's say a second, it will be at the equilibrium position. While it's not, even though it's not moving in this direction, this is me recording it every second that goes by. So, for example, after 1 second, it will be right here. And then after another second, it would have reached this point. So this is what I'm seeing here. Then after another second, it would have gone back up into the equilibrium position. So it will go back into 0. So this is after another second, for example. This is an example, by the way, that I'm going through for you to understand. So I'm plotting now every second that goes by in which location it is. And then after another second, obviously, it would have gone back to the original position. So back up. So if we assume that it's roughly somewhere there. So you see I'm plotting the points and then joining them together, and I get a curve that looks very similar to the displacement distance graph. These are two different graphs. Now, in this case, I can extract two information from this. I can extract the amplitude, because once again, I'm showing the displacement from the undisturbed position, so from the rest position. So this can give me amplitude just like the other graph can. But I can't get wavelength from this because this is time, this is not distance. So what I could get is how long it takes for one oscillation to take place. So that means I could get the period from this point to this point. And in this case, we used an example of a second each time it moves up or down. So that will be a period of 4 seconds. And since I know the period, I can also get the frequency. And that gives me, for example, what I will need to use later on. So if I have both graphs, I could really get the wavelength, I could get the period and hence the frequency, and I could calculate it using this equation. Frequency times wavelength. This is the going a step ahead. This is going a bit, further in terms of your knowledge and application of using graphs, using the definitions and putting it all together. Before I move on to some exam questions, I thought we'll go through the target points that you need to make sure that you're aware. So for targets 1 to 4, you should be able to identify wavelength and amplitude from a displacement distance graph, define frequency, calculate the speed of water waves. If you want to get higher grades, so 5 to 7, then you should be able to describe how wave speed can be derived from the definition of wavelength and frequency. And for grade 8 to 9, you need to be able to derive the wave speed equation. Now, I didn't make it very explicit before, but if you have a look back at the definition of wavelength and frequency, now the wavelength is a distance from one point on one wave to the equivalent point on an adjacent wave, and the frequency is how many of those waves are passing a point per second. So just to simplify this a bit, if this is the distance that the wave travels, and I have about, for example, 8 waves passing that point per second, meaning I have a frequency of 8 Hertz, then I have 8 of these waves, which are, let's say, wavelengths of 2 meters. So if I have 8 of those waves passing a point in 1 second, that means I have 8 times 2. Now, also, if you would pay attention at the units, this is wavelength is in meters and frequency is in seconds. So meters per second is what actually you end up with here. So if we go back to considering the equation for speed is equal to distance divided by time, in this case our wavelength and the amount of waves passing a point per second. So we have the wavelength, which is actually the distance of one wave. And then we have the frequency, which is the number of these waves passing a point per unit time. So my time is left here behind. So the total of distance covered by the amount of waves, it simply gives me the distance, and then how many waves pass a point per second gives me the per unit time per second, basically. Now we're going to look at, obviously the rest of these things involve calculations. The better way of looking at that is more through exam questions, which I will go through now. So starting with this diagram, it shows a water wave drawn to scale. What is the wavelength of this water wave? Now remember what we said about wavelength. If you want to keep it simple, pick the same point. So I'm going to pick this point to this point, and it is a distance between those 2 points. I will also consider where the undisturbed line is, where 0 is. I'm just going to draw my line there so that I don't miss that out. So what I have is from this point here, from this point to this point. So this gives me 4 and 8. So the distance between those 2 points is 4. So that's 4 centimeters. What is the amplitude? Remember the definition for the amplitude is the displacement from the undisturbed position, which my undisturbed position is here. So I need to take it from the top to 0, which is here. So that will be from 0 to 3. So that's 3 centimeters there. It says then 12 waves. And remember, always the questions gives us clues, and we need to keep track of those clues. It says 12 waves pass an observer in 4 seconds. So it told me the number of waves, and it told me in how long, in seconds. What is the frequency of the waves? Remember, frequency is defined as the number of waves passing a point per second. So now we just divide the two. So that's 12 divided by 4. So the frequency is 3 hertz. So I have 3 waves passing a point every second. It says to show clearly how you work out your answer and give the unit. Very important. So that will give you the mark there. And it says for question 2, a note was played on an electric keyboard. The frequency of the note was 440 hertz. What does a frequency of 440 hertz mean? So this is once again checking your knowledge of the definition. So we said frequency is the number of waves passing a point per second. So in this case, if I have a number, I can say that it means that 440, since this is an electric keyboard, that's sound. So that's longitudinal waves if you want to say it, or you just say waves or vibrations. So 440 waves produced in 1 second. So you could say vibrations or oscillations as well. The next part says the sound waves produced by the keyboard travel at the speed of 300, so this is my V, my speed, 340 meters per second. Calculate the wavelength of the note and give your answer to 3 significant figures. So here I have my speed given to me. I need to find the wavelength. In the previous part, because this is part 2, if you think that there's clues missing from the question, then just please go back to the previous parts and read them again. They will be there. So you were given the frequency to be 440 hertz. You need to recall and apply the equation and rearrange it. So you need to rearrange for wavelength. So I will divide both sides by frequency. Since I'm multiplying, if I want to get rid of the frequency from next to the wavelength to make wavelength the subject, then I need to divide both sides by frequency. Frequency divided by frequency is 1, and that leaves me with this. So that's 340 divided by 440, and that gives us 0.773 hertz. 3 significant figures, 1, 2, 3. Meters. And the unit, because its wavelength is meters. Now, this is one of the questions that actually test a lot of your knowledge in a more intense way. This is from an A-level question that I took it, but it's very, likely to pop up in GCSE exam questions too. It says figure 1 shows the variation with time of a displacement of 1 point in a progressive wave. Then figure 2 shows the variation of displacement of the same wave with distance. So we have the displacement distance graph and a displacement time graph. This use figures 1 and 2 to determine the amplitude of the wave. Let's remember what amplitude is. It's from the rest position to the maximum displacement. If I look at both of them, they're both, because it's the same wave, so this is the same wave that we're looking at. So the maximum point is 0.6 from 0, and here the same thing, 0.6 from 0, so that will be 0.6 millimeters. Both graphs give me amplitude. Then it says to determine the wavelength of the wave. Remember, wavelength is in distance, so we can't use this graph, that's time. I'll pick a point from here to here, or you can do it from here to here, is your choice, or from here to here, depends what you prefer. In this case is 0. That's 0.05, 0.06, 0.07, 0.08 meters long. The frequency of the wave. Now remember what we said before. There is no axis that says frequency or wavelength or anything, so you will need to remember this. But if I have the period, time period, which I can get from this graph, then I can find the frequency, since frequency is 1 over period. So let's look again. The same way we'll get wavelength, we'll also get the period. So from 0 to 42, 44, so that's 44 milliseconds, because I need to also look at the units from the graph. So that will be 44 times 10 to the minus 3, because that's milliseconds. So milliseconds simply means times 10 to the minus 3 seconds. And you need to remember your unit prefixes, and you need to memorize them if you still don't. Once you do the calculation, you will get about 22.7, which is about 23 hertz. Now you can calculate the speed of the wave. Do you have the wavelength? Yes, you do. Do you have the frequency? Yes, you do. So frequency times wavelength is 23 times 0.08, which gives you 1.82, and to two significant figures as 1.8 meters per second.